In this video, we're going to see some fine examples of the derivatives of exponential functions. So to begin, here are the rules that we're going to need. Now, once again, if we're working in base e, the natural base, that's what's going to be easiest for us, because the derivative of base e to the x is just the same as it ever was, e to the x. And the derivative of that is e to the x, the derivative of that is e to the x. The derivative does not change the exponential function at all. However, if you choose to work in a base other than base e, let's say you're working in some arbitrary base a, where a is a real number greater than 1. The derivative of a to the x is going to have a to the x in it, but there's going to be this pesky multiplicative term, the log, the natural log of the base a, whatever base you're working in. That's going to be a constant multiple that pops out in front of the copy of the exponential function that you were deriving. Keep in mind that in base e, the natural log of the letter e for base e, the natural log of e is 1. So if we let a equal to e, then this constant term right here just becomes a 1, and so that's how we get the e to the x. That's our easiest base, so I would definitely prefer you working in base e. Alright, now before we begin, I'd like you to also recall some exponent rules that we have, and these are not only true for base e, but these are true for any base that you're going to use, but I will commonly, most usually work in base e. If you have e to some number a, and you multiply that by e to some other number b, what happens is, you actually have e raised to the a plus b power. Okay, so if you multiply two functions in the same base, you get that base raised to the sum of the powers. Likewise, if you're going to divide two bases, if you're going to take e to the a and divide it by e to the b, then you're going to get the difference. E is going to be raised to the a minus b. Notice that this is really the same thing as that over there. If you see 1 over e to the b being the same thing as multiplying by e to the minus b, because it's on the bottom, that's why the exponent is negative, and so that's why the b has a minus in front of it here. Okay, hopefully this is coming back to you. And then the last one is if we raise a power e to the a and raise that to the b, then we get e to the a times b. So when do we ever multiply two exponents together? When do we end up with a times b? That's when we've raised e to the power a and then raised that to the power b. If we're going to multiply two bases together, that's when we add the powers. Now keep all those rules in mind as you're working with the problems, because sometimes you can use those to simplify the math before you begin taking the derivative. Okay, so once again, we're going to find some derivatives, and once again, usually we're going to need the chain rule, because unless I'm going to ask you an easy one like what's the derivative of e to the x, some of the harder ones that I can ask are going to be a composition of functions, which is to say I'm going to take e and I'm going to raise it to something other than just x. Here I've raised it to 5 times x. Okay, so that's going to be the chain rule whenever we have a composition. Keep in mind that the chain rule is always in effect, and it will often be employed when taking the derivatives of logarithms and exponentials. However, this first one doesn't need the chain rule, because you can see the base e is simply raised to the x. It's not raised to a function of x. And then I just put a 5 in front of it. So this one you're just going to be using the constant multiple rule, and I just want to test to make sure you understand the basics before we make it more complicated. So go ahead and try this one, and also try this one before I give you the answers. Did you try them? I hope so. Okay, so this first one, like I said, pretty easy one. The 5 is just multiplying it in front, and so the 5 is just going to stay out in front, and then we're going to take the derivative of e to the x. But the derivative of e to the x is simply e to the x. So the derivative of 5 times e to the x is still 5 times e to the x. See, it looks like I didn't even do anything, which to some people may think that they might think they did it wrong because it looks the same, but you didn't do it wrong, because the derivative of e to the x is e to the x. So that's indeed the correct answer. Okay, what about the next one? This one we actually had to use the chain rule, because when you take that derivative, it's not raised just to the x, it's raised to a function of x, 5 times x. Okay, so we got to use the chain rule. How do we begin? We say we have e to some stuff. Well, the derivative of e to some stuff would be e to that same stuff, right? So the derivative of this starts with just repeating what was given to us. But wait, don't forget the chain rule. So what is it that I'm forgetting to put here? That's right, a times 5 right here. This times 5 comes from the fact that the derivative of 5x is equal to 5. So that's why 5 pops out right there. And so the answer to this one is 5 times e to the 5x. Okay, now let's pretend we were working in some other base for some silly reason. We weren't working in base e. Maybe we were working in base 10. Let me redo these in terms of a different base so you can see how this rule plays out. Okay, so instead I'll change this problem to say 5 times 10 to the x. And on this problem right here, let's say I have 2 to the 5x. Okay, now these are different bases. This one is working in base 10, this one is working in base 2. Go ahead and take those derivatives again, keeping in mind that the rule is very similar. A to the x goes to a to the x, but just a constant pops out there, the log of a pops out. Okay, so see what we got here. Like I said, it's going to be the same answer that we would have got, which is going to be 5 multiplied by 10 to the x, because that's the base we're working in. However, we have to keep in mind that if we're not working in base e, the natural log of the base we're working in is going to appear in the answer. So this is also multiplied by the natural log of 10. Or if you like to write it this way, it's 5 times log 10 times 10 to the x. Alright? And keep in mind, the 10 to the x is the functional form part of that function. That's the only part that has x dependence. The rest of this, 5 times log 10, is just a constant that comes out in the front. Okay, what about down here if we were working in base 2 and we had 2 to the 5x? What's the derivative of that? Just like before, the first thing we're going to do when we take this derivative is we're going to copy down what we had. And then don't forget the chain rule. So we have to multiply by 5 because the derivative of 5x is 5. And then don't forget that if you're not working in base e, in any other base, you're just going to have that pesky constant that's going to come out in front. So this is also multiplied by the natural log of 2. Or some people prefer to write this as 5 log 2 times 2 to the 5x. Okay? So see how these are almost the same as the ones in black here, except the base has changed. And coming along with the fact that the base has changed, we have this multiplicative term, natural log of the base we were working in, when we take those derivatives. Okay, so that's just to illustrate what happens if you work in a different base, but I will now go back to base E, because most of the problems you encounter will be in base E. And now, I'm going to give you some more complicated ones, and sometimes some of these might require rules other than the chain rule. The chain rule is going to be the most common rule that we will have to employ. However, sometimes we will find ourselves in a situation where we need the product rule, like right here, x squared times e to the 2x. We have a product. We have x squared times e to the 2x. So we're going to need for this one the product rule. So the fact that f times g prime is equal to f prime g plus g prime f. Okay? And then over here, this next one, e to the 4x plus 1 divided by e to the x. Now this one, part D, looks like a quotient, so we might have to use the quotient rule, but I really don't feel like it unless I really am forced to use the quotient rule. Turns out this one has a denominator that just has a single term. So instead of using the quotient rule for this one, I would recommend trying to divide this part by that denominator and separately divide the 1 by that denominator. And here, I'm trying to give you practice with this exponent rule right here. So this is one in D here that I would simplify first to avoid using the quotient rule. Okay, so try that out. And then another one here, let's say we have e to the 4x plus 2 to the 8th power. Alright, so if you remember the time that we spent with the chain rule, most of the problems that we had involving the chain rule, well, a lot of them anyway, were like some function and then in parentheses raised to a high power, right? And then the power comes down and you leave that stuff alone to a lower power times the derivative of the inside. So this is like one of our classic chain rule problems right here. Okay, pretty much every single one of these is going to use the chain rule, but sometimes it must be additionally used in conjunction with another rule, such as the product rule here. Go ahead and try these yourself. Definitely want to see what you would write down on your own before you just go into looking at the answers. Are you trying? Okay, good, good. So let's see what we got on this one right here. X squared is going to be our f. E to the 2x is going to be our g. And we have to use the product rule. So f prime is 2x multiplied by g, which is e to the 2x, plus, now when we get to the g prime, that's the part where we have to take the derivative of e to the 2x. And remember, a lot of times we're going to have to use a chain rule. In this case, the e is raised to 2x, not just to 1x. So we have to use a chain rule. So the derivative of e to the 2x is e to the 2x times 2. And then the f, we're just leaving the f alone, that's the x squared. Okay, so the g prime here is e to the 2x times 2 because e to the 2x goes to e to the 2x, and then chain rule tells us multiply by the derivative of the inside function. The derivative of 2x is 2. Okay, so that's the derivative we get for C. Is that what you got too? Nice. On D here, you could use the quotient rule, but notice I didn't even write it down because you don't actually need it. You can first just simplify this first, okay? So if you didn't try that yet, go ahead and try this right now. I'm just going to simplify it and then I'm going to take the derivative, okay? Here's a rule right here. So this rule tells me that if I took e to the 4x and divided by e to the x, that's going to simplify. And if I take 1 and divide it by e to the x, actually I could rewrite that in terms of a negative power so that this would all get simplified out. So what I was looking for here is that e to the 4x over e to the x turns into e to the 3x. And 1 over e to the x can be rewritten as e to the minus x. That's what I meant by simplify. Is that what you got? Great. So, that's all before I take the derivative. Notice I didn't surround it in parentheses. Oops, I should have done that to this one. And then prime it. So as soon as I surround it in parentheses and prime it, that's when I start taking the derivative. This whole line was just simplifying. And now that I've got it simplified, I'll just leave that one part here. That's e to the 3x plus e to the minus x. Now I'm going to go ahead and take the derivative. That derivative, after simplification, is the same as that derivative, and this is something that's going to use the chain rule again. E to the 3x goes to e to the 3x times 3, and e to the minus x goes to e to the minus x times minus 1. So this is 3e to the 3x minus e to the minus x. That's the derivative that we get for that one right there. So far so good? Hopefully you're feeling good about this, okay? And then this one goes back to our classic chain rule problems where we have a bunch of junk raised to a power. So to enact the chain rule, we're going to call this the inside function, and we're going to call stuff to the 8th the outside function. Okay? So when we take the derivative of all this stuff, first the 8 comes down, and then we leave that inside function alone, just leave it just how we found it, and we're going to raise it to one lower power, so 8 minus 1 is 7. Did you get that part? Okay, so far so good. Don't forget the chain rule. We must now multiply this by the derivative of this inside function. Alright, and the derivative of e to the 4x plus 2 is e to the 4x times 4. And the derivative of plus 2 is 0, so the 2 just goes away and it disappears. But once again, you see that when we have e to something times x, we repeat that, but then we have to multiply by the number that was multiplying the exponent, the x inside. Right? So then if we just combine the 8 with the 4 into 32, we get 32, and then I'll bring the e to the 4x to the front, and then we get the quantity e to the 4x plus 2 to the 7th. Okay, so I prefer to write it this way. That's just common practice for mathematics, but this is also a correct answer on this line too. Alright, so I hope you're enjoying these.